Hi, everyone. So I'm Andrei from Zama. I'm a machine learning director for the team that builds Concrete ML. So my talk today will be about how Concrete ML enables confidential decentralized AI. So decentralized AI is a platform to execute AI workloads such as inference or training on public infrastructure. It uses the blockchain to process, to distribute, and to store data that is used to train or to predict for machine learning models. And it uses for both the compute and the storage, it will use a decentralized network of nodes. And these nodes are actually just computers that can be located anywhere in the world. So using decentralized AI, we have the advantage of being able to scale to a large number of nodes. So that means having a large throughput for the AI workloads. And it also means that we can bring down the cost of AI applications compared to centralized approaches. However, because we're using public infrastructure, decentralized AI exposes user data and model parameters to the public. So when these data and parameters are confidential or sensitive, there could be many lost opportunities unless privacy can be guaranteed. So people might be afraid that their data will be leaked. So people could, or it could be companies that are afraid that their confidential data is leaked, or people that worry about their personal data, personally identifiable data. So they might be afraid of using these services. So that's why privacy is so important to enable the services to be used on a large scale. So Concrete ML is a machine learning framework that converts models that work on clear data to FHE programs that implement the same type of functionality, inference or training, but on encrypted data. And Concrete ML does this by using FHE, Fully Homomorphic Encryption, which allows processing of our data in its encrypted form without decryption. That means that only the owner of the secret key can read the results of the machine learning model inference, or can get back the trained machine learning model. So a machine learning model that was trained on their sensitive data. So Concrete ML enables encryption of data sets and model parameters. And it supports both inference and training on chain. So that means that training and inference can be implemented as smart contracts to orchestrate the distribution of the AI workloads. And these smart contracts can pull in data either that is stored either on-chain or off-chain or something like IPFS and is linked on-chain. So all of these use cases are possible. We can store large amounts of data off-chain and use them in the smart contracts because with FHE we can provide access control to this data. Also, a very cool feature is that Concrete ML works with existing decentralized AI protocols. So, as we shall see just in the following slides, this is very useful because we don't just need to ensure the privacy, but we also need to verify the computations that are done and provide access control to the data and to the results of the model predictions or to the results of model training or data analysis. So, with privacy, we enable a large array of use cases. For example, in healthcare, we can think about patient records that can be stored on-chain and that over which we can provide services such as AI diagnosis or collaborative medical research. So when using an encrypted blockchain, we can also provide collaborative features because using a public key infrastructure, we can process data coming from multiple users and provide insights that can only be obtained by aggregating information coming from many users. Advertising, well, if you look at the Web2 advertising, it's using third-party cookies, which have a terrible privacy record. And moving these advertising services to be on chain, we can preserve privacy because we can store in an encrypted form all kinds of useful information such as purchase histories or user preferences, which can then be used to provide targeted ads. And all this is done securely without actually exposing the information because we're processing all this sensitive information in its encrypted form. Biometrics relies on some of the most sensitive information on about an individual that we can think of, such as, for example, photo of their face, their ID, iris signatures, or even their DNA. So this must be protected with the highest level of we must ensure the highest level of protection through cryptography. And this information, if it's encrypted, then with FHE, it can also be used to provide useful services, such as identification. For example, when you open a bank account, you are required to submit a photo of your ID. This can be done on-chain by storing the photo of the ID in its encrypted form. Finally, for finance, using AI, we can provide some useful decentralized finance applications, such as credit scoring and fraud detection. This can be implemented using machine learning models that look at information about the credit score applicant, applicant, and we can also analyze transactions to detect fraud. So we talked about the privacy that they can be provided by encryption, but because we're using public infrastructure, we also need to handle verification of the computations that are done by worker nodes. We are protecting the data, but we also need to ensure that the models or the AI applications were performed correctly. So luckily, to do this verification, we can rely on systems and on protocols that already exist on the blockchain. For example, consensus. With Concrete ML, we are processing ciphertext, and the resulting ciphertexts are deterministic, so we can perform computations multiple times. Classical consensus approach, and then we can do some majority voting to identify if the computations were performed correctly. Next, optimistic fraud proofs rely on staking. So for fraud proofs, basically, in a certain window of time after second computation is performed, anyone can challenge the correctness of a computation. If they submit a proof that the computation is incorrect, then the worker node that performed the computation will lose the money that they staked to obtain that workload. Finally, cut and choose is pretty similar, but is faster. In a similar approach, but here we're only verifying small parts of the computation. So Concrete ML can expose all of the intermediary values used in a computation, and then a verifier can only check a random sample of those values. So that's much faster. It's much faster, and that's one of the interesting features to have for the verification is that the time spent to prove the computation is low. Okay, so we talked about privacy and verification. The final piece of the puzzle is access control, because we're storing data on the blockchain in encrypted form, and we also store the results of the model computations on chain. So we want to ensure that only authorized people have access to this data. So to do this, Concrete ML works together with the second Zama product called the Threshold KMS. The Threshold KMS can ensure that there's some authentication needed to use to decrypt a ciphertext and to use the value of that ciphertext. And we can thus create an access control list that is propagated to the results of any computation, for example, computation done using ConcreteML or other computations, so that we can protect all the, not only our data, but also the results of processing of our data. So let's look at the more technical aspects of ConcreteML. So ConcreteML is an open source framework built for data scientists. And the good news is that you don't need to know any cryptography to use ConcreteML. So all the cryptography parts are handled behind the scenes. And the users of ConcreteML only need to have data science knowledge. So we implement many types of models. For example, linear models, tree-based models, neural networks are the most classical ones. And we all, of course, also support large language models, which are the most popular ones being used today. Finally, we also support the data frame style API to do pre-processing of data. So let's look at the APIs. This is the big selling point for ConcreteML. APIs are very simple and they're very similar to what data scientists use in their on classical data science projects. So if you look at these code samples, you can probably recognize that it looks very much like scikit-learn. So in scikit-learn, you have this very common pattern where you call fit to train a machine learning model, and then you call predict to apply the model to new data, new test data. So this is what it looks like for a developer of ConcreteML. First, they do the classical data science part, train the model, test it out on new data, and then they compile the model. This is the new part. They compile the model to an FHE program that will implement the same function as the prediction function or the training function on encrypted data. So then it's possible to predict on encrypted data. So this is the predict call with the FHE equals execute flag. Here we show two models. Now for an example with LLMs. For LLMs, what we currently support is computing some of the models, some parts of the models with FHE, and some parts of the models on the client side. So just to go back a bit, so I just want to mention, so this is what it looks like for the developer. So here, both the training and the prediction, the conversion to an FHE program is done on the developer's machine. So when you want to go to production, this predict call here will change, because on the developer's machine, this predict call actually hides the three stages: encryption, execution of the FHE program, and decryption. So when you're working in a client-server approach or in a decentralized approach, you want to split those stages, to split those stages so they are executed on different machines. So for LLMs, for example, we execute different parts of the model on the client machine or on the server machine or on worker nodes in a decentralized network. So here we make a list of the layers of the LLM that will be executed remotely. And we have this very helpful very helpful hybrid FHE model class that handles the orchestration of this execution, calling remote nodes, calling or remote server, doing encryption, decryption, and all the local computation that still needs to be done to perform the full LLM model inference. So here's the result with Llama. Just some output from Llama with the model that we compiled. Just asking it what is FHE. We get a pretty decent result. We clipped it because in reality it's really long. Very thorough explication here. So and this is what the code for Llama looks like. The Llama has a very large number of layers, so we're using a filter on the Llama layers to choose which ones will be executed remotely. So the decentralized layers here, we fill this up with all the layers that match these patterns. Then we compile this hybrid model, and we execute it to do all the orchestration and communication necessary to produce a token based on user input. Okay, so some other use cases. Sentiment analysis is also a very popular one. So here we're taking a phrase or a paragraph, and we want to know what the predominant sentiment in this text is, a positive, neutral, or negative one. So this phrase will be analyzed with a transformer model to produce features, and then the classifier will be executed to predict the three classes. So first we encrypt the sentence, and then we will do apply the model in FHE. So this is what it looks like to implement this kind of sentiment analysis. So here we're looking at the classifier part, and what I would like to pinpoint here is the use of classical tools from scikit-learn to optimize the model, to have the best trade-off between accuracy and latency with FHE. So here we're trying out different hyperparameters for the model using what's grid search, which is a typical approach in data science. So we can use this concrete ML classifier to do grid search. Once we find the best combination of hyperparameters, we compile it, and then we deploy it with tools that are integrated in concrete ML. Okay, another example would be anonymizing documents to then send them to ChatGPT to do, for example, retrieval augmented generation. So we would like, ChatGPT is not encrypted, so your data can be stored, can be reused by OpenAI. So if you want to have full control of your data, one approach is to anonymize it. It's not a perfect approach. Ideally, we would like ChatGPT to be encrypted. But to still use ChatGPT with less risk of exposing your sensitive user data, you can use anonymization. And the good part is that we can do anonymization on encrypted documents with concrete ML. So you can take your initial document, and you want to basically redact some of the sensitive information in it. And for this, we built a demo. We show how this can be done. This document will be encrypted, and then a machine learning model will be executed to produce a redacted document that then which is then sent to ChatGPT to perform retrieval augmented generation. So to implement such an application, here we're showing using what we call our client-server API. We're showing the client side. So basically, we're extracting tokens from the documents. We're encrypting them, and then we're sending them to the server to be processed to get back a decision for each word, whether it contains sensitive information or not. Okay, one more application, DNA processing. So again, DNA data, this is highly sensitive. You don't want this floating somewhere on the internet. So if you want to have some analysis of your DNA data, encryption is probably the best approach to preserve its confidentiality. On the client side, you will have a genome, which will be encrypted. And here we will show how this is quite complicated machine learning pipeline. Actually, it implements some research papers on DNA ancestry. It contains multiple classifiers, and this is it will show one of the advantages of the FHE scheme that we use at Zama. What we use at Zama is TFHE is an FHE scheme which is composable, which means that you can produce, let's say, do a computation and then do any number of new computations on the results of the previous ones, and you can do this infinitely. So that's a very helpful feature to have, and it's applied here in this application. Because in this application we're using, I think it's about 400 classifiers in the first stage, and this is the training code used for these classifiers. So first we're training a number of base models on different parts of the genome, and they each produce an intermediate decision, and then we train a final smoother classifier. And this one will aggregate the decisions of the previous ones. So we have a huge number of classifiers, and they all work sequentially on the user's DNA. And to implement them, actually this is pretty much it. The code is really quite simple. All the complexity is hidden away behind this fit and predict functions here. Okay, so as I said, Concrete ML is an open source framework. So you can check out all of the code on GitHub and submit any issues if you have them. And we have the documentation and demos, and we're really looking forward to see what you guys will build with Concrete ML in the decentralized AI space. So thank you very much. Are there any questions?
Yeah, thank you. It's a very nice presentation, and obviously there's a immense value of doing machine learning on end-to-end encrypted data. But help me really understand, like, how does blockchain fit in? Like, what's the value? Like, two aspects that I think about from your first half of the presentation. One is data living on chain. So even if it's encrypted, what's the real benefit of that data being on chain? And then the second aspect of consensus that you mentioned, right? So, I mean, doing AI on with a large model is already cost prohibitive. So what's the real benefit of having multiple agents do that inference and then do a consensus of that, as opposed to just trust a service provider?
Okay. So I think there are two sides to the question. So the first one is we can think about what blockchain can help for AI, and we can also think about how what AI can do for blockchain. So it's two different questions, because you might have smart contracts that can use AI features. For example, a simple thing, to open a bank account, you need to verify your identity. So that might involve some AI functionality. And you want to have that functionality on chain to be able to have this transaction that will authorize you to open a bank account. So then this is what Concrete ML can do, provide these functions that integrate into smart contracts. Okay, so that's one side. And the other side is blockchain for AI. Well, blockchain can help us build a decentralized AI platform. Because, as you well said, there are some performance issues with FHE, so it's definitely slower than processing data in the clear. But if we are to split the workload of the workloads necessary for AI, actually we can have a pretty good latency in the end. If there are sufficient worker nodes, we can have a latency that's not too bad compared to processing data in the clear. And blockchain can help distribute the tasks, distribute the data, and incentivize people to perform the work needed to do to fulfill the AI computations. the overhead of FHE can be greatly reduced in this setting. As I showed with the hybrid model approach, we are splitting up the LLM into many parts, and this can be sent to individual worker nodes, and then the intermediate results can be reassembled to aggregate to obtain the final prediction, which is basically a token, a generated token. We can also see how we can also do fine-tuning of models. So here, the latency aspect is a bit, so the constraint on latency is a bit reduced. You might wait a bit more for your training to end, but not that much. In any case, it's not on a real-time application. And training on encrypted data is very useful, especially when you're training on data coming from multiple parties. And this is very, very simple when you're using a blockchain. Compared, if you were to do this with traditional methods, it's a lot more complicated. Either you set up MPC, which is complicated, and you need to implement the functionalities specifically for depending on your applications. With concrete ML, it's basically you program just like a data scientist. And also with the blockchain approach, the key management is greatly simplified. So there are many things that make AI and blockchain actually benefit each other. Yeah, one more question.
So first, I agree with you. This is much bigger than just blockchain. And my question is, I know that hardware acceleration is coming. What will be possible to do ML-wise, let's say in the next year? What can you cover?
Yeah,
with concrete?
But using a large language model on encrypted data on chain to generate tokens, for example, or to fine-tune some of these models, I think in 1 year's time, even maybe sooner, will be doable with a cost that's not much higher than doing the same thing on clear data, provided that the decentralized network has sufficient nodes, obviously, and that let's say that we can't predict if some new model comes out which is very, very different from what we have today. That might pose a problem. But with the current models that we have today, Llama 7 billion, Mistral, I think they are doable today in a decentralized manner with acceptable latency for token generation. So in some months' time, up to 1 year's time.